If you've come across a headline claiming James Webb discovered 900 billion stars have mysteriously vanished from the universe, here's what you should know before watching any further. That specific claim doesn't check out. It traces back to low-quality blog posts, not NASA, not a peer-reviewed journal, and not any named observatory. The quote attached to it from an astrophysicist at something called the Space Science Institute doesn't appear in any legitimate scientific publication or NASA press release. It's the kind of story that gets copy-pasted across dozens of clickbait sites and YouTube channels, worded almost identically each time, with no actual data behind it. But here's what makes this worth talking about anyway. Buried underneath that fabricated headline is a real phenomenon, one astronomers actually do study, called missing or homeless stars. Stars that exist right where you'd expect them not to. Completely outside any galaxy at all, drifting alone in the space between them. And in June 2026, James Webb genuinely did make a real discovery involving exactly this kind of star, in a galaxy cluster so unexpectedly developed that it's forcing astronomers to reconsider how quickly massive structures actually formed in the early universe. This is the real story behind the exaggerated headline, what intracluster light actually is, why finding stars floating loose between galaxies matters for understanding dark matter, and what James Webb just found 10 billion light years away that's got astronomers revising their models. Start with the actual phenomenon at the center of this story because it's stranger and better documented than any invented headline needed to be. Galaxy clusters, the largest gravitationally bound structures in the known universe, can contain thousands of individual galaxies, all held together by their combined gravity, and by an even larger amount of invisible dark matter surrounding them. As those galaxies orbit each other within a cluster over billions of years, they occasionally pass close enough that their mutual gravity rips stars directly out of one galaxy and strands them in the empty space between galaxies entirely, no longer bound to any single one. Multiply that process across billions of years, and an entire faint, diffuse glow builds up throughout a cluster made of countless individual stars belonging to nothing. Astronomers call this glow intracluster light, and it was first proposed as a real phenomenon back in 1951 by astronomer Fritz Zwicky, who noticed unexplained excess light between galaxies in the Coma cluster. It took decades of steadily improving telescope technology before scientists could reliably confirm and measure it. Here's why intracluster light has been so difficult to study, even decades after Zwicky first proposed it. It's extraordinarily faint, typically less than 1%, as bright as the natural glow of Earth's own night sky, meaning it gets easily lost in the noise of any telescope not specifically sensitive enough to tease it apart from everything else in an image. For most of the 20th century, astronomers could really only detect it indirectly, comparing overall brightness measurements and inferring that some fraction of a cluster's total light didn't belong to any individual galaxy. Actually, resolving and mapping that light directly required exactly the kind of extreme sensitivity the James Webb Space Telescope was built to provide. That's exactly what a team of astronomers accomplished in a set of 3 related studies published in the Astrophysical Journal Letters and presented at the 248th meeting of the American Astronomical Society. Their target was a distant galaxy cluster called XLSSC 122, first discovered back in 2014 when the European Space Agency's XMM Newton X-ray Observatory detected an enormous amount of heated gas glowing at that location, a telltale sign of a massive gravitationally bound structure. Follow-up. Roughly 10.4 billion light-years away, meaning the light reaching Earth's telescopes today left that cluster when the universe itself was only around a quarter of its current age. Even those early Hubble observations hinted at something odd. The cluster already looked unusually mature for something existing that early in cosmic history. James Webb's observations, led in different parts of the effort by astronomers, including Kyle Finner at Caltech's Infrared Processing and Analysis Center, confirmed just how unusual XLSSC 122 actually is. Webb detected clear, unmistakable arcs of warped light stretching across the cluster, the signature of strong gravitational lensing, where a massive foreground object bends and magnifies the light of galaxies sitting even farther behind it. Those telltale arcs simply weren't visible in the earlier Hubble images at all. Finner described the moment the team first saw them in Webb's data plainly. Seeing strong lensing coming from a cluster this distant set a new record, making XLSSC 122 the most distant galaxy cluster ever confirmed to produce this kind of dramatic gravitational lensing effect. Strong lensing matters here for a specific scientific reason, because it's driven almost entirely by a cluster's dark matter, the invisible material that makes up the majority of its total mass. Measuring how strongly and precisely a cluster bends background light gives astronomers a way to weigh that dark matter directly without ever needing to see it. Finner explained that strong lensing works essentially as a way to measure dark matter without actually seeing dark matter. calling it a sensitive probe for testing existing models of how the universe evolved. Webb's data let the team measure the concentrated mass at the cluster's dense core this way, while a second, complementary technique called weak lensing, which produces much subtler distortions spread across a much wider area, let them measure mass extending out through the cluster's less dense outer regions as well. But it's the third paper in this set that connects most directly back to the original missing stars idea, because it's specifically about intracluster light, the glow produced by exactly the kind of homeless, tidally stripped Hyungjin. This study represents the earliest, most distant confirmed detection of intracluster light ever made, found glowing faintly around XLSSC 122 at a point in cosmic history roughly 10 billion years in the past. Using Webb's exceptional infrared sensitivity, combined with Hubble data and careful modeling to separate out contaminating signals, the team detected diffuse light, extending several 100,000 light years from the cluster's central galaxy, dim enough that it registered at roughly 29 magnitudes per square arc second, an almost imperceptibly faint glow that simply wasn't detectable with the instruments available before Webb existed. Across the different wavelengths Webb measured, this stripped starlight made up a median of roughly 17% of the cluster's total light, a substantial fraction for a structure existing this early in the universe's history. That number matters because of what it implies about timing. Building up that much intracluster light requires repeated galaxy interactions and mergers, violent gravitational encounters happening again and again over an extended stretch of time. Finding it already well underway just 10 billion years ago suggests galaxy clusters were assembling themselves, merging and shedding stars into the space between galaxies considerably. Earlier, and considerably faster, than many existing models of cosmic structure formation predicted. There's also a genuinely elegant piece of physics tying this specific discovery back to dark matter directly. The research team noticed that the shape and location of the intracluster light in XLSSC 122 lines up closely with the concentrations of dark matter mapped out through the cluster's gravitational lensing. Finner described the O's relationship directly. In this particular cluster, the intracluster light essentially traces the dark matter, and that overlap itself indicates the cluster is actively in the middle of a merger. A separate paper in the same set, using data gathered from the Chandra X-ray Observatory, the Meerkat Radio Telescope, and the ALMA array, alongside Webb's own observations, identified a consistent elongation running across the cluster in one specific direction, along with an offset between where the hot gas and the total mass are concentrated, additional independent evidence supporting the same conclusion. XLSSC 122 isn't a settled finished structure. It's still actively merging, still in the process of coming together, even though it already looks in many respects more like a mature, modern-day cluster than anything astronomers expected to see this early in the universe's history. If that pattern turns out to hold up in other distant clusters as researchers gather more data, intracluster light could become a the faint stray light of stars that have been ripped loose from their original galaxies. That's the real scientific promise sitting underneath all of this, considerably more interesting and considerably better supported by actual evidence than any invented story about hundreds of billions of stars simply vanishing without explanation. It's worth being clear about what remains uncertain here too, since that's exactly the kind of distinction the fabricated version of this story skipped over entirely. Researchers have not concluded that XLSSC 122 is somehow unique or impossible to explain within current cosmological models. What they've said, in Finner's own words, is that finding a cluster this evolved this early is forcing scientists to refine those models, not abandon them, and that the genuinely useful next step is finding more clusters like it. As Finner put it, it's still early in the JWST era, and if astronomers can gather comparable data on tens or even hundreds of similar objects at this same stage of the universe's history, that growing sample would let researchers properly stress test their models of cosmic evolution, rather than drawing sweeping conclusions from a single unusual example. That distinction between one surprising data point and a confirmed, settled revision of cosmology is exactly the kind of nuance that gets lost whenever a real, interesting finding gets flattened into an exaggerated, fabricated headline instead. The actual science here doesn't need any invented drama. A cluster of galaxies, photographed as it existed roughly 10 billion years ago, already showing signs of the same kind of stellar stripping and dark matter structure seen in clusters much closer to our own time, genuinely is a meaningful, still unfolding puzzle. One astronomers are actively working through using real, verifiable observations, rather than a single dramatic, unsourced claim about 1 trillion stars disappearing overnight. XLSSC 1-22 isn't an isolated case either, which is part of why the underlying science here is more interesting than any single headline could capture. Webb and other modern instruments have been turning up multiple galaxy clusters over the past couple of years, each case adding another piece to the same broader picture. The European Space Agency's Euclid Space Telescope, a mission specifically designed to map the large-scale structure of the universe, conducted its own detailed study of intercluster light in a cluster called Able 2390, using Euclid's wide field of view and faint light sensitivity to trace how that diffuse stellar glow is distributed throughout the cluster structure. Separately, researchers analyzing Webb observations of a cluster called PLCK G165.7 plus 67.0 applied a similar intercluster light subtraction technique, not to find stray individual stars this time, but to uncover point-like sources hiding within that same faint background glow. Dense, ancient collections of stars called globular clusters. After carefully modeling and removing the diffuse intercluster light, and then accounting for background objects that could be mistaken for genuine cluster members, that team identified an estimated 793 likelies. Globular cluster candidates drawn from an initial sample of more than 900 point sources. That number is worth pausing on for a specific reason. It's a small, almost ironic echo of the very story this entire discussion started with. The fabricated 900 billion missing stars headline invented a figure with 900 billion attached to it, and no real research behind it at all. The actual verified research happening in this exact area of astronomy really does involve counting objects in the hundreds, several hundred previously unconfirmed globular clusters, tens of thousands to hundreds of billions of individual stars making up a cluster's intercluster light fraction, real numbers tied to specific instruments, specific clusters, and specific published papers. The genuine science was never short on impressive figures. It just required actually doing the work of measuring them properly, rather than inventing a headline number and attaching a fictional expert's name to it afterward. It's worth understanding, too, why fabricated stories like the original 900 billion missing stars claim manage to spread as persistently as they do, because it says something useful about how to evaluate space and science headlines more broadly. James Webb genuinely does produce a constant stream of legitimate, exciting discoveries, which creates an environment where an invented claim, written in a similar tone and citing a similarly official-sounding institution, can blend in easily alongside real news. The version of this story that's been circulating since early 2025 borrows real scientific vocabulary, deep fields, galactic evolution, dark matter, and wraps it around a completely unverifiable quote attributed to an institution and a person that don't appear connected to any actual published research on the subject. That's a pattern worth recognizing broadly. Specific numbers and named experts don't automatically make a claim credible, especially when no legitimate observatory, university press office, or peer-reviewed journal is the actual source. There's also a genuine, real scientific mystery involving missing matter that long predates this fabricated story, worth mentioning simply because it's easy to conflate the two. For decades, astronomers grappled with what's sometimes called the missing baryon problem, the observation that roughly half of all the ordinary, everyday matter the universe should contain, based on careful calculations from the early universe's radiation, couldn't be directly accounted for in visible stars, galaxies, and gas. That mystery was real, well documented in peer-reviewed research, and gradually resolved over the past several years as astronomers developed techniques using fast radio bursts, extremely brief powerful pulses of radio energy from deep space to detect and measure faint, diffuse gas spread thinly through the vast spaces between galaxies. Gas that turned out to be hiding the missing material all along. That's a genuine example of matter appearing to be missing, and later being accounted for through careful, verified research, an entirely different, legitimate story from the fabricated stellar disappearance claim this video opened by correcting. It's worth circling back to Fritz Zwicky for a moment, because his own career adds an interesting layer to this story that connects directly to dark matter itself. Zwicky is the same astronomer who, decades before Vera, Rubin's own more famous galaxy rotation measurements, first proposed in the 1930s that galaxy clusters seem to contain far more mass than their visible stars and gas could account for, some of the earliest evidence ever put forward for what would eventually be called dark matter. That same astronomer's 1951 observation of unexplained excess light in the Coma cluster, the very first proposal of what we now call intercluster light, means two of the most important open questions in modern cosmology: the nature of dark matter and the existence of homeless intergalactic stars, both traced back to the same researchers' work, separated by only a couple of decades, and both still being actively investigated using instruments Zwicky could never have imagined would exist. Another real example worth mentioning comes from one of Webb's very first published images of a cluster called SMACS 0723, released as part of the telescope's earliest public data back in 2022. Even in that initial release, astronomers noticed something they hadn't fully anticipated: hundreds of faint, point-like sources clustered near the massive galaxies at the image's center, candidates for either stripped galactic nuclei or compact globular clusters, along with additional small, unresolved structures elsewhere in the image that researchers proposed could be compact star-forming regions, or, in cases of extreme gravitational magnification, potentially even individual stars made briefly visible through lensing. That early result, obtained essentially by accident within days of Webb's first images going public, was itself a preview of exactly the kind of systematic, carefully verified intracluster light and globular cluster research that would go on to produce results like the XLSSC 122 findings years later. From Webb's very first look at a galaxy cluster, evidence of homeless, tidally displaced stellar populations was already sitting there, waiting for researchers to develop the techniques precise enough to properly measure it. There's a broader lesson in what happens next scientifically, too, one that's considerably more interesting than any fabricated ending could offer. XLSSC 122 isn't being treated as a closed case. Astronomers involved in this research have specifically framed it as an early example of what they hope becomes a much larger, systematic effort, using Webb's sensitivity to hunt for similar strongly lensing, unusually mature clusters at comparable distances, then measuring their intracluster light and dark matter distributions, the same careful way this team did. Each additional cluster added to that sample tightens the constraints on existing models of how quickly structure actually assembled in the early universe, gradually replacing a single surprising data point with a genuine statistical picture. That's a slower, less immediately dramatic process than a single headline claiming hundreds of billions of stars vanished overnight, but it's also the process actually capable of answering the underlying question. A story like that pretends to already have solved whether the universe's earliest massive structures came together the way current cosmology predicts, or whether, as clusters like XLSSC 1 and 22 hint, they got there considerably faster than anyone expected. It's also worth appreciating just how quickly this whole area of research has moved since Webb first launched. When Webb's earliest images of SMACS 0723 went public in 2022, clusters spotted in that field were treated as an interesting curiosity, worth flagging for future study, rather than something researchers could confidently characterize in detail. By 2025 and 2026, that same basic capability had matured into a full, systematic methodology, careful coma and intracluster light subtraction techniques, multi-instrument cross-checks using X-ray, radio, and gravitational lensing data together, and confident, peer-reviewed measurements, like the 17% intracluster light fraction found in XLSSC 122. That's a genuinely fast turnaround for an entire subfield of astronomy, going from an intriguing anomaly in a first light image to a repeatable, quantifiable measurement technique in under 4 years. And it's a large part of why, being early in the JWST era, the tools needed to properly answer these questions have only just become available, and the pace at which they're already producing results suggests the next few years of this specific research are likely to move quickly too. So here's the real story once the fabricated version gets set aside entirely. James Webb didn't discover 900 billion stars vanishing from the universe. What it did discover in June 2026 is something considerably more grounded and, in its own way, just as remarkable. The earliest confirmed evidence of stars torn loose from their galaxies and scattered into the space between them, glowing faintly enough that no telescope, before Webb could have ever hoped to see it, in a cluster that shouldn't, by most existing models, have looked this developed so early in the universe's history. Nothing about those stars disappeared. They're exactly where the physics says they should be, homeless, drifting, and now, for the first time, finally visible.